In the lab this week, we'll be working with various light emitters and receivers. And you've already worked with the emitter, an LED. The cool thing about having both of those is you can make a little optical link, and now you can get a signal from one place to another on photons, and that's just incredibly cool. It's also sometimes incredibly useful. Perhaps you want to get a signal from one place to another and have two systems be completely electrically isolated. Maybe they have to be isolated because there's some dangerous voltage. Maybe you're on opposite buildings. Maybe one of them's on a satellite. Optical communication, in other words, is an aspect of what we're doing. This fits into a lab about RC filters and frequency response because these links, one of the most important things you're going to want to know about them is how fast can they go. So we're going to characterize different receivers, different photo detectors, as a function of their speed, and we'll see that they're quite different. So I'm going to briefly introduce the physics of a couple of these because it will help you use them to understand a little bit of why one's fast and one's slow, and also it turns out they talk to you electrically quite differently. So the first of those that we're going to work with is a photoresistor. And a photoresistor, as it sort of sounds like, would have a symbol something like that. If a physicist was doing it, they would write H nu there, which is the energy of a single photon. And the resistance of this device changes when you drop light onto it. The physics of that, the physics of almost all these devices, is based on the semiconductor. The semiconductor, like silicon, or its brothers and sisters in the semiconductor family, are these incredibly powerful materials that sometimes act as insulators and sometimes act as conductors, and that makes them very useful as switches and amplifiers. In this case, as a photoresistor. So we don't quite have all the physics to get the details, but the basic idea is if you looked inside this as a black box, when photons come in, they start creating electrons that are more free to move. These are little E minuses. You can think of the device, it's the semiconductor, as having electrons that are normally tightly enough bound that the voltage that you would put across this does not have enough energy to pull them away from their parent atoms, and so they just slosh a little bit in this potential well of being bound to the nucleus of their particular atom, but they don't move. And that's the definition of a resistor, pretty good one. But when you put light on it, the light is absorbed in this semiconductor, and if you remember your chemistry and spectroscopy, the photon has to be absorbed by a particular atom, and what happens is the electron will jump up an energy level. And the next energy level up, it turns out, in this material is one where now, when you put reasonable voltages across here, those electrons are higher up in their potential well, and they can move, and they will conduct. So you generally will see that the resistance goes down as you put light on these materials, and the resistance itself is a function of that light. When you turn the light off, the electrons will fall back into whatever the closest little potential well is. They'll drop down in an energy level, and once again, they're hard to move.